or afternoon. Hi, my name is Gavin Schmidt and I'm going to talk to you about climate change, particularly the climate changes that we're seeing this year and last year, and how we understand the changes that we have seen in both temperatures and sea level and extreme events over the last few decades, and particularly what that's going to mean for the future. So here are the questions that I'm going to use to kind of frame this presentation. So what are the drivers of climate change, right? What are the things that are changing, that are causing the climate to shift? Are things changing faster than we predicted, right? So if we look at the observations, if we look at our model projections for the future, are these things out of line or otherwise in question? And what happens next, right? And I'll talk about the drivers of what's going to happen next, but also the physical constraints that allow us to make those predictions. So first of all, let's start off with the fact that climate has changed. This is a picture of the Mendenhall Glacier, which is in Alaska, and it was a picture taken in the late 19th century, in 1894. We could have picked any old pictures of ice, frankly, and it doesn't really matter where we would take it from. But you can see, this is a glacier that is coming down from the mountains there. And if we go back today and take a picture at exactly that same spot, we see something very, very different. And as I said, we can go to almost any part of the world where there was ice, where there are old photographs, whether it's the Alps, Hokkaido, the Himalayas, the Andes, the mountain glaciers in Africa, in Kilimanjaro, the mountain glaciers that used to exist in Papua New Guinea. We can go back and look at those same places and we can see that the ice is disappearing. We can see that the climate that allowed those glaciers to exist has changed, right? And everywhere we go, we see this. And so clearly something has changed, and we can see it in the records of just the changes in the planet that we see in front of us. For the modern period, we can do better. We can actually instrument this. We can measure the changes in real time. These are changes that are calculated from ICESat. So this is changes from a laser altimeter that is kind of from a satellite going down. It measures the height of the ice sheet, bounces back up. And we can see that over the last few decades, the changes in Antarctica, mostly in West Antarctica, so that's the bit just to the left of the Antarctic Peninsula, have been very, very large. And we can see that in Greenland, pretty much everywhere around the edge of Greenland is losing mass and losing height, and everywhere in the middle is gaining height. And we can actually track the total amount of mass in Antarctica and Greenland by measuring their gravity. Right, so how much mass can be detected from space and how those changes over time are happening can be tracked. And we can do that for Antarctica, and we find that it's losing on average about 150 gigatons of water every year. And in Greenland, it's even larger. It's about 250 gigatons of water that's being lost from the Greenland ice sheet every year. Okay, and each of those things are adding to sea level because it's extra water that is falling into the ocean, raising the levels everywhere around the world. The weird weather that we have been having, particularly in 2023 and continuing into 2024, has really been exceptional. This is a graph of the temperature anomalies over the last 100 some years, starting off in 1880. Every line is an individual year, and the blue lines are the years in the 19th century, and the red lines are the years most recently. And you can see that 2023, which is that uppermost line, kind of departs from the pack very, very dramatically, starting from around this time last year, and was significantly warmer than all other months previously. And in fact, we have now had 12 and possibly 13 months of straight record-breaking temperatures. Every month for the last year has been warmer than all of those months in the instrumental record. And that instrumental record goes back to the late 19th century with some confidence. So 2023 was special. Right, and we don't really know exactly why, and I'll get back to that a little bit later. In particular, the summer last year and then the fall was extremely warm, and we have temperatures of about 1.3 to 1.4 degrees Celsius over the pre-industrial period, or the late 19th century, and so that's the warming that we've seen in roughly 140 years. And you can see the pattern. It's very clear. It's everywhere. It's in the tropics. It's on land. It's in the Arctic. It's in the Southern Ocean. And there are very few places that had a colder than normal year last year. And the trend that we're seeing is extremely large. We can see that different estimates of these, we can see that different estimates of these temperature changes over time put together from weather stations and ocean data and the like all tell a very, very similar picture. There is a lot of up and down as you go through the years. Those are caused by El Nino events or volcanoes or the weather, effectively, mostly. But then there are these long-term trends, right? We see that it was kind of flat for the first 40 years here. It kind of rose and it got warmer through to the 1940s, then it kind of cooled slightly to the 1970s. But after the 1970s, we've seen this very large and seemingly relentless growth of temperature until we get to 2023, which, as I mentioned, was an exceptional year and was by far the warmest year in the record. And in fact, it broke the record by a record-breaking amount. And so that is certainly something that matters, and it isn't just an intellectual exercise. This could be something that we measure, but that doesn't really have any impact for the real world. But let me give you one extra number that can put this in context, and that is the fact that these temperature changes are about the size of a quarter of the difference between the last ice age and the present day, and the modern period, right? So if we go back 20,000 years, the world was in the grip of an ice age, the last glacial maximum. There was the sea level was about 400 feet, 120 meters lower than it was now. All that water was in the ice. It was in the ice on the large ice sheets in Eurasia, Fenno-Scandinavia, and in North America. And the temperatures at that time globally were only about 5 to 6 degrees Celsius colder than the pre-industrial. And so we've warmed up by around 1.3 degrees Celsius, and so we were talking about a quarter of the difference between the pre-industrial and the last ice age, and now in the other direction we've warmed that much in only 100 years. And it's worth pointing out that the last ice age took about 10,000 years to warm into the Holocene period that we were, until very recently, part of. So these are really big numbers. They might not seem big, right? You know, you're looking here 1.3, 1.5, 2 degrees Celsius. These numbers might not seem very large, but in the context of the planetary temperature, they are absolutely huge. And so the concern that climate scientists and others have is that these are very, very large and significant numbers that we've been measuring, and we continue to measure. I mentioned before that the impact of the melting ice has been to raise sea level, but the sea level is also rising because of the amount of heat that's going into the ocean. And so as the ocean warms, it expands, and that raises the level of the water, as well as the water that's coming in from the ice sheets and the mountain glaciers and the like. And that's leading, obviously, to coastal flooding. Right? This is Miami, which is notorious in the US for having increasing amounts of what are called clear sky flooding. So flooding that's just happening at high tide that is beyond what people have historically seen. And we can go around the US and we can examine how many more flood days a year we're getting, and as sea level rises, what we're seeing is an exponential increase in the number of flood days per year. And so that means that we are seeing real impacts of coastal flooding rising from almost nothing to something that's going to become ever more significant, even though the rises in sea level seem like they may be steady. But the impacts of those rises of sea level are going to be increasing exponentially. How do we go about trying to understand why these things are changing? Right? How do we go about trying to understand the causes, the drivers, the impacts, and making the projections? Well, we start off with what are called climate models, right? So we have been working on climate models collectively since the 1970s, and back in the day, these were made with very old computers, punch cards, no screens. Everything had to go in, one line of code at a time. And while we no longer use punch cards, we still use Fortran, and we still basically code the models in very similar ways that we started coding them 40 or 50 years ago. But obviously those models have become much more sophisticated, they're much larger, and they're much more skillful. The way that this has worked is that people started off with relatively simple models of radiation in the atmosphere, the dynamics of the weather, the dynamics of the ocean, the composition of the atmosphere, how much gases, how many aerosols there were, what was happening in the stratosphere, what's happening in the soils, what's happening to the carbon cycle. And over time, all of these things have been amalgamated and put into what are now called coupled climate models, Earth system models sometimes. And these are models that try and include all of the things that we think of as being important, but put together so that we can see how each of those different modules, each of those different processes impacts all of the others. And so we have models now that are made up of very detailed reductionist estimates of what happens when sea ice forms and reflects sunlight, or when snow occurs, or when clouds form and dissipate and rain out. All of those different, very, very small scale models are all put together, and then we try and examine the emergent properties of this system, and then compare those emergent properties of this modeled simulated system with the real world. And over the years, what we have done as a community is set up comparisons of all the different models that we have, starting in the 1990s and going through to efforts that really just recently concluded with what's called the Coupled Model Intercomparison Project, so CMIP, and we've just done phase 6. So CMIP 6 is the latest generation of these models. And these models, like I said, combine many different aspects of the climate system, and the idea is that we can all run them in relatively similar ways. So groups in Japan, groups in Europe, groups in the US can all run their models, and then we can compare those models both to each other, that's the intercomparison part, but also to the observations, right? So we do these historical estimates, we do these projections for the future, and the idea is, well, we can compare these models, this multi-model ensemble of models, to what's actually happened in the real world and what that implies for the future. How do you build a model? Well, the basic idea hasn't really changed for very long, but basically you start with the inputs, like the boundary conditions. Where are there continents? How high are the mountains? Where are there trees? Where is there a lake? You know, those kinds of things. What's the shape of the Earth? What's the orbit of the Earth? All of those things are external boundary conditions that help set what the climate is on the planet. We then try and build the things that we can calculate a priori, so the dynamics of the fluids, both in the ocean and in the atmosphere and in the sea ice. And then we try and parameterize the things that are too small scale for us to be able to do a priori. And so those are things like the, how fast does cloud form? How fast does it dissipate? How fast does it rain out? What happens when you have a lot of turbulence in the boundary layer? How much water evaporates? How much heat gets transferred? All of those things are what are called parameterizations. We put those into the model based on process level data as best we can find it from the real world, and then we put it all together and we have a look at the whole globe, and then these are models, right? So there are a few parameters that you can tweak. Right now what we're doing is we run perturbed physics ensemble, so we change all of those variable parameters, and then we use machine learning to help us calibrate the model so that we can find the most accurate model given a set of parameters. And then once we have that, we can then evaluate the model. How well does it do, not just on the global patterns of clouds or rainfall or something like that, but how well it's matched the observed changes as a function of time. And we always find problems, and so then we go back and we revise the model inputs, we revise the parameterizations, we retune the model and do the evaluation again. And that cycle continues to produce models that are more and more skillful, but they're always still imperfect and incomplete. So what do these models look like? Well, here's an animation of this. What you're looking at here are particles in the atmosphere. So they're giving you a sense of what the atmospheric circulation is in these models. The orange is dust that's being wafted from the Sahara across the Atlantic. You can see the blue is the sea salt that's being whipped up by storms, in this case in the North Atlantic. The white is pollution that's being emitted from mostly from the burning of relatively dirty coal. The green that you're seeing is organic aerosols. They come from biomass burning or from forests and the like. And you can see here, there's a lot of activity. You can see some tropical cyclones in this case, and those tropical cyclones look blue because they pull a lot of salt into the atmosphere. Each of the red dots is a fire, and so that's a source of what's called biomass burning emissions. So that can be soot, organics, or smoke, all sorts of other things. And you can see that this is a very complex dance, right? You can see the storms moving the sea salt around. You can see the tropical waves moving moving things in the tropics. You can see the pollution getting wafted around. And the interesting thing about this is that while it's clear that the weather, which is being generated here by the model, is moving all of these different components around, these components, because they're visible, because they interact with radiation, they interact with clouds, they're also impacting the climate itself. And of course, we just saw a volcano go off there north of Madagascar, and that is a natural phenomena that also adds to the complexity of what it is that we're seeing. And so we can look at these pictures and we can dive in, and there are 1,000 different stories that we could pull out from such an animation. And that's the kind of thing that we do with these models. So, have these models proved skillful? Like, have they given predictions that worked out for the most part? And the answer is yes. But I'll give you some examples. So back in the 1960s, the seminal paper by Manabe, who was famously a Nobel Prize winner, born in Japan, but did most of his work in Princeton and GFDL in New Jersey. Back in the 1960s, he made some very clear predictions about what would happen when we increased the amount of carbon dioxide in the atmosphere. And one of the key things that he found was that the troposphere, that's the lower part of the atmosphere, would warm, right? But the stratosphere, the bit above the weather, the bit where the ozone layer is, would cool. And in fact, it would cool quite dramatically. And this was a prediction that was made before we had any measurements of temperature changes in the stratosphere, right? So this is a purely model-driven prediction based on basic physics. The first circulation models, the first climate models that did transient runs, so where you would let it step forward year by year and you would see what would happen, came about in the mid 1980s from the group at GIS, which is where I work now, from Jim Hansen in 1988, and again from the group at GFDL, led by Suki Manabe, like just a year later. And the predictions that they made were that the land would warm faster than the oceans. The north would warm faster than the south, and the Arctic would warm most of all. And so those are very clear and actually robust predictions from even the earliest climate models. And they made some additional predictions that would allow us to determine whether, if we got those predictions right, whether we were getting them right for the right reasons. And the key thing that people highlighted, even in the 1980s, was the importance of measuring the heat in the ocean. And it turns out that if the climate is changing for the reasons that these models thought that the climate was changing, basically the increase in greenhouse gases leading to a reduction in heat leaving the planet, and then more energy coming in, net energy coming into the planet. Where does that energy go? That energy has to go into the ocean. And so if we could measure how much energy was going into the ocean, we'd be able to tell how much, how sensitive the climate was, and whether these models were actually making those predictions for the right reason. And Hansen said here that the best opportunity for a major improvement in our understanding of climate sensitivity, which is how much the climate will warm if we increase the amount of carbon dioxide, is monitoring the internal ocean temperatures. And back in the 1980s, we did not have this data. right? We had not put that data together. Some of it existed, but we had not put that together in large enough databases for us to be able to determine what those trends were. And so that was a high priority going into the 1990s. Could we do that? Could we measure the temperature changes in the ocean to sufficient precision to be able to tell whether the ocean heat content was in fact rising? I should probably give you a slight discussion on what it means for a model result to be skillful. I use that word quite deliberately. All models are wrong, right? They are approximations, they are incomplete. And so the issue is not are climate models right? They're not right, they are wrong. But we want them to be skillful. Are they giving us better predictions than what we would have had without them, right? And so that's the test. And it's the same with weather forecasts. Weather forecasts are not perfect, right? We know that the prediction for tomorrow is better than the prediction for in 3 days or 5 days or 7 days. But we do have a sense that weather forecasts are skillful. They tell you something that you would not have been able to work out just by looking outside the window, right? They can tell us when there is a front coming across the country. They can tell us when there is a typhoon or a hurricane barreling towards the coast. We can see with a weather forecast that skill, right, being better than what you could have done without it, is absolutely the key metric for whether a weather forecast is useful. And it's the same for a climate forecast. Are the climate forecasts that come out of climate models better than what you would have guessed just by sticking your finger in the air and guessing? And the answer is yes, and I'll give you a couple of examples. So I mentioned the stratospheric cooling and the tropospheric warming. Now we have satellites that can measure these things, and we have satellite records of these things from the late 1979 all the way to the present. And those blue lines at the top there, they show the cooling in the stratosphere from like 15 kilometers to about 50 kilometers. And then the ones, the red and the browns at the bottom, those are the temperatures in the troposphere, and you can see that they have been warming. And so each of those is a nominally independent estimate made up from multiple different satellites all stitched together, but it clearly shows the skill in that initial prediction that came from Manabe and Weatherald in the 1960s. The patterns of climate change, recall the pattern of predicted climate change was that the land would warm more than the ocean, the north would warm more than the south, and the Arctic would warm most of all. And that is exactly what we see. These are the trends over the last 40 years, showing that very, very clear pattern. There's a few places here where the warming is not extremely clear yet. One of these places is right near the Southern Ocean. We could discuss that a little bit later perhaps. And then the tropical Pacific has not warmed quite as much as other parts of the planet. But the overall pattern, given the crudity of the models that were being run in the 1980s, is extremely well captured. In terms of the predictions of global mean temperature, back in 1981, we had predictions, and in fact, the real world has warmed faster than what we predicted in the 1980s. In 1988, 1984 was when these models were run. Those predictions turned out again to be skillful, better than what we would have had without that. The first set of multi-model runs, these are the CMIP3 models that were run just past the year 2000. Those have a 20-year plus record of correctly predicting what the temperatures in the global mean were going to change, how they were going to change. And again, we did this again for CMIP5, and again, the models predicted what was going to happen to the temperatures with some fidelity. And then that key prediction about the ocean heat content, well, what happened there? Well, it turns out that we have been able to bring together an enormous amount of data, digitize that data, deal with the corrections in that data for non-climatic things, changes in instrumentation, changes in calibration and the like. And what do we see? We see very, very clearly that the amount of heat content in the ocean has been rising by an enormous amount of heat. This index on the side here is 10 to the 22 joules. That's 10 to the 21 is a zettajoule. So this is hundreds of zetajoules, which is an mind-bogglingly large amount of water, large amount of heat, and people have tried all sorts of ways to try and get people to understand how much heat this is, but it is a lot. It is a lot of heat, and it's very clear. It's very clear that the oceans have warmed, and they haven't just warmed at the surface. They have warmed throughout their depth, almost all the way to 4,000 meters depth. And so all of the predictions that were made in the 1980s and earlier have in fact come true. And so we're very confident that the predictions that we made, we got those right for basically the right reasons. Now we can look in more detail, and here's an animation, and what I'm going to show here is an attempt to attribute those changes, right? So there's going to be 4 lines going across, and we're starting off right at the top is the stratosphere, and then it goes down a little bit to the lower stratosphere, the surface, and then the ocean heat content at the bottom, and then there's the Arctic ice area at the top, and there's going to be 3 sets of model runs here. So one set of model run is only going to have the natural changes. So these are things like volcanoes, or the wobbles in the Earth's orbit, or the solar cycle. All of the things that have absolutely nothing to do with us, that would have happened regardless of our activities. And then there's another line which is going to be what we've done, so the contributions to the climate changes that have been led by human activity. So that includes deforestation, changes in air pollution, changes in greenhouse gases, irrigation, all those kinds of things that we have been responsible for. And then we're going to put all that together, and we're going to say, okay, well, what happens when you have all of our activities, the human activities, the anthropogenic activities, and the natural activities, and then we're going to compare that to what actually happened. And so we don't have, this is going to go back from 1850, we're going to go forward. We don't have great data from the 1850s, but as we get to the more modern period, we'll see more and more observations come into play, and then you can see whether we can match all of the things that have changed from the top of the atmosphere to the ocean heat content, and from the poles to the tropics. So there's a lot of noise in these things. You'll see in the stratosphere, you'll see some big changes. There you saw something there which is associated with volcanic eruptions. They warm the stratosphere, cool the surface. You can see in the surface temperature, you can see some oscillations in the tropical Pacific, which is associated with El Nino and La Niñas. In the ocean heat content, there's not very much going on, but as you start to get into the 1990s, 2000s, things start to become much more clear, right? So the changes that you see in the ocean heat content anomalies, they only occur in the runs that have our input, the anthropogenic runs. The changes in the surface temperatures only occur when you have the anthropogenic causes. The changes in the stratosphere only happen in the anthropogenic runs. The changes in Arctic ice area only occur in the anthropogenic runs. And so when you put everything together, which is the blue lines here, you actually get a very good match, not just to some of that interannual variability, but also to those long-term trends. And so when people ask us how much of these trends are due to our activities, the answer is all of it. People don't often understand that. But all of the trends that we're seeing in the large-scale pictures of climate are because of our activities. There is solar cycle activity, there is volcanic activity, there is interannual variability because of El Nino and La Nina and the rest of it. But the long-term trends over the last few decades, 50, 60 years, all of those trends are due to us. I mentioned that the models that we use have over the years got better, and so these are different generations of the models, CMIP 3, CMIP 5, CMIP 6, roughly every 5 to 7 years. You can see that on average, the error is getting less. There's more skill. The wilder models have been effectively pruned, and the best models are getting better every generation. And this goes even for things that we haven't really tuned for or targeted. So these are correlations of climate patterns associated with El Nino or the Pacific decadal oscillation, which is a pattern of temperature change in the North Pacific. And you can see the light blue with the correlations with the observations in the earlier models. The red is with the next generation, and the dark blue is for the latest generation. And you can see as these things move along, they move into higher correlations. And so the skill in these models, their ability to match the patterns of change that we have seen or that we can see in the real world has been getting better with every generation. And so models have been getting better, but the basic result that we just saw in the animation and in those earlier predictions, the basic result that the increases in greenhouse gases for the most part are driving the changes that we're seeing has not changed. So what is happening now? Last year we had a very low Arctic sea ice extent, so that was in the southern hemisphere winter, so that's like kind of June, July, August, September. That is the maximum, generally speaking, for the Antarctic sea ice, and it was way lower than it has been in previous years. This year is not quite as low, but you can tell already that it is quite low and will be probably the second lowest sea ice extent by the time we get to the end. If you look at the temperatures, you can see the orange line is the really standout year from 2023, and you can see that the black line is now 2024. We're kind of getting to the point where 2024 is going to be a little bit cooler than 2023. But you can see that the last 2 years have really been very, very exceptional. And as I said, we've had record warm temperatures now for over 12 months straight. And that's leading to bigger impacts, right? So this is an estimate of the serious disasters in the United States. It's a little bit of a weird calculation, but it gives you a sense, I think, of what's going on. How many events pass a threshold of $1 billion costs? And you can see that over time this has been increasing, and it's been increasing both because there's more stuff in vulnerable areas, but also because of things like the green bar there, which is severe storms. Those are effectively flooding events driven by extreme precipitation. And those are increasing very, very rapidly over time. And so last year, 2023, had the highest number of events that crossed this threshold and had the highest cost in terms of what the damages were. And part of this is due to the fact that we can now look at individual impacts of individual extreme events, and make a probabilistic statement about how much more likely or less likely they were to occur because of climate change. And all of these red dots that you see on this map this is a compilation from Carbon Brief, which is an excellent website that tracks these things. Each of those red dots is an event where there has been a specific attribution study done, and people have said, well, you know, given this frontal system coming in, given this storm system coming in, how much worse was the damage? How much more extreme was the event? How much more intense was the event because of the change in the background climate? And for things like heat waves, it's clear that we're seeing many more and more extreme heat waves all around the world. Changes in rainfall intensity. We're seeing increases in rainfall intensity, again, pretty much everywhere around the world. We're seeing changes in snow events. So sometimes we're seeing larger snow events, but less snow overall. And we're seeing trends in that. We're seeing changes in what we call agricultural drought, so how much water is in the soil, but we're not seeing it everywhere. So there are a number of places and a number of kinds of events where we haven't yet been able to detect an anthropogenic component. And mostly that's related to very noisy events like rainfall, total amounts of rainfall. That's very noisy year to year, decade to decade, and it's very hard to see that the impact of the anthropogenic changes to temperatures or to water vapor have had a huge impact on that. And so a lot of the blue dots there where we haven't found an anthropogenic increase in intensity or magnitude, that's because the time series of rainfall are very, very noisy. But you can see that there's a whole suite of extreme events that are happening to people all over the world that do now have a recognizable anthropogenic impact on them. And so the temperature changes that we've seen so far, right, which is about 1.3, 1.4 degrees Celsius since the pre-industrial, they have had an impact not only on those global means, but nobody lives in the global mean. They're actually having impacts on weather events that are being experienced locally by people in Tokyo or in Europe or in South Africa or in America. Now, one of the things about 2023 that was strange is that at the beginning of the year, there's a number of groups that use a multitude of methods to predict what the year is going to bring. And in each case, they were way too low. Nobody predicted that 2023 would be as warm as it turned out to be. And so Schmidt, that's me, I have a prediction based on the long-term trends and the state of El Nino at the beginning of the year. The Met Office has a very elaborate modeled estimate of what's going to happen. And in neither case, and the other two are based on similar statistical methods to my own. In none of these cases did we meet the actual 2023 temperatures, even at the extreme of our uncertainties, right? So way beyond our 95% confidence in what we were doing. Now that's interesting, right? So that implies that there was something happening that was not included in those models. And so there are really still open questions as to what that is going to do. One small caveat is that the 2023 temperatures, which you can see is the last dot on that point, are still within the bounds of the climate models, right? So the climate model trends over time. 2023 was not outside of the realm of possibility, but the details of what happened in 2023 and ongoing into 2024 are very different to what any of the particular models showed. So there may be other factors. So what are those other factors? There was an eruption from the Hunga Ha'apai volcano near Tahiti that increased stratospheric water vapor by about 10%, which is a massive amount. This is an underwater volcanic explosion that the plume went something like 56 kilometers into the stratosphere. It put both ash and sulfur dioxide and water vapor into the stratosphere, and we haven't quite worked it out exactly yet, but we think that there was enough sulfate to provide a cooling. That's what happens with a lot of big volcanoes, but the stratospheric water vapor is a greenhouse gas, and so that provides a warming. And so the different estimates have that the volcano may have cooled the climate a little bit, or it may have warmed the climate a little bit. So we still need to do a little bit of work on that. One of the other things that people have been looking at is the changes in sulfur dioxide from ships. So in 2020, there was a new regulation that ships had to reduce the amount of sulfur in their in the bunker fuel, and they did so pretty much from one month to the next, and that led to about an 80% decrease in the amount of shipping emissions. And because the shipping emissions would produce sulfate aerosol, that's reflective, that's a cooling factor, plus it interacts with clouds, which extends the clouds, and so we expect therefore that reductions in the pollution should warm the climate a little bit. And we're starting to see some estimates of that coming out, and people are coming out with numbers like I don't know, like 500ths, maybe 800ths of a degree Celsius warming globally because of these changes. And if we look at the 2023 numbers, the 2023 was out by everybody's calculations by about 0.2 degrees Celsius. So we're looking for 0.2 degrees Celsius to explain what's going on. And so the Hunga Tonga eruption on its own, I don't think that's going to do it. The marine shipping emission change, that's probably not going to do it. Solar cycle, we're going into a solar max right now, and that's a little earlier and a little larger than predicted, and so that might have given us, again, around 500ths of a degree in 2023. So one could imagine that you add these things up, plus a little bit of El Nino, plus a little bit of this and that, and we can explain it. But nobody's actually done that yet. So we don't yet have a proper accounting for what happened in 2023, and it matters because obviously the Hunga Tonga eruption isn't something that's going to stick around for very long, and so if it's because of that, then we're going to go back to what we predicted. The changes in shipping emissions, those are probably permanent, and so that's going to be an offset that's going to continue on, but probably not get any worse. The impact of the solar cycle, that comes and goes. And so if these are the causes of what happened in 2023, then we can have some confidence that the long-term predictions from the climate models are going to be fine. If, however, we're seeing something else, if, however, we're seeing the climate react in ways that we didn't expect, then that might mean that the climate model predictions that we have for the future might not be so great. But we still have to see about that. Now, that goes to the future. And there's a great quote which I like a lot. If we had observations of the future, we obviously would trust them more than models. But unfortunately, observations of the future are not available at this time. And so when it comes to making predictions, we can't use observations, we need to use models. What are we going to do with those models, and how do we build credibility in those predictions? So here are some predictions that came from the last estimate from the CMIP6 efforts. This is with one particular model that I've been involved with, and you can see there that you have a good match to the historical period, right? So the historical period is the purple lines, before 2014. The observations, you can see the black dots on there. That goes to 2022. 2023 is kind of in the middle middle of the lines in the orange area. And then you've got these four scenarios, and they're given kind of tricky technical names, but you don't really need to worry too much about what that means. You can just think of them as the one at the bottom is heroic efforts to reduce emissions, and that would be compatible with the Paris Agreement. All the way up to the one right at the top, which is a scenario where people effectively want to burn it all. Like burn all the hydrocarbons you can find, all the oil, all the tar sands, all the methane hydrates, all the coal, just burn it all. And we would be capable of doing that, but hopefully that is not actually what's going to happen. But the temperature changes that you can see, right, this is baseline to the pre-industrial. The most optimistic scenario that we ran there ends up with temperatures around 2 degrees warmer than the pre-industrial, and the worst case scenario that we ran has temperatures around 5 degrees warmer than the pre-industrial. And if you recall, 5 degrees cooler than the pre-industrial was the last ice age. And so if we were to do something as crazy as that high-end scenario, we would have warmed the planet as much as the ice age was cold, but in the space of 100 or 200 years. And that's really astounding. Are we expecting then the warming to accelerate? This is a graph from a paper that got a lot of attention last year, and it comes from Jim Hansen, who was one of the key pioneers back in the 1980s, and he's still writing papers and involved in the science. And he predicted in this paper that we were about to see an accelerated warming, where if you just took the linear trend from the last 40 years and then extrapolated that forward, that's that green dotted line, the warming would be more than that. And people were quite concerned. How realistic is that? Are we going to see this accelerated warming? Have we already seen this accelerated warming? And the answer is let's see. It's worth, however, looking at those models, right, to see whether the models are also predicting an accelerated warming. The answer is yes. So the orange lines, the yellow lines there is the same as the yellow lines in Jim's paper, and the dotted line is that same linear prediction. And so the models, and the average of the models is that red line. The models are saying yes, we do expect that we will be a little bit off that linear trend for the next 10, 20, or 30 years, assuming that the scenarios and the emissions continue basically without pause. And so the answer is, the answer to the question, do we expect that the temperatures will increase if we don't change course, or will accelerate if we don't change course? The answer is yes, we do expect that. It comes both from Jim's estimates, it comes from the models themselves, and so that is something that one might be able to expect. However, detecting acceleration with just the real world data is much harder, because it's a lot noisier. And so if you try and do a quadratic fit through this data, you can't really detect an acceleration so far. But do we expect it once we have enough data? The answer is yes. But the key thing to remember, right, and this is something that's really only become clear in the last decade or so, is that future warming is a function of future emissions. And let me kind of walk you through this, because this is, I think, a little counterintuitive to what people sometimes think. So the first graph here is it's a schematic of what might happen, right? So we've been increasing the amount of carbon dioxide, and that's been increasing, right? So we're well aware of that. And now this is a counterfactual, right? So the question is, what would happen if we suddenly got to net zero? If we suddenly reduced carbon dioxide emissions from human activities to zero, right? And then we kept it there. right? What would happen? Well, what would happen to the carbon dioxide concentration in the atmosphere is that it would start to decline, right? We'd no longer be pumping it up, and it would start to decline. It wouldn't go back to the pre-industrial levels for a while. It takes a while for the carbon cycle to soak up that carbon, and most of all, I mean that's going to be sucked into the deep ocean. But you're going to see that decline in carbon dioxide in the atmosphere. That would be very clear. The heat uptake in the ocean, we mentioned that was increasing as a function of climate changes. So that rate of change of heat uptake would start to slow, right? So we'd see that going down, and that would get to zero by the time you got to an equilibrium state. But what would happen to the temperatures? Right? The interesting thing is that the temperatures, the global temperatures, our best estimate is that the global temperatures would plateau. If we cut emissions to net zero tomorrow, the temperatures in the global mean would no longer rise. Right? And that's what's called this zero emissions commitment. Right? And that means, and it turns out that it doesn't matter when you stop the emissions. At the point where you get to net zero, global warming effectively ceases, right? So so we could get to net zero. Obviously it's not going to happen tomorrow or in 2030, but maybe by 2050, maybe by 2080. At the point we get to net zero, temperatures will stop rising. Now that means that the impacts of the high temperatures, they don't go away, but they don't get any worse. And some things are what are called lagging indicators. So sea level will continue to rise, albeit at a slower rate. But the consequence of all of this calculation is that any emissions that we have going forward that are more than net zero are actually contributing to the temperatures that we'll see. And so you can conclude that future warming is a function of future emissions. And that's quite sobering, because it means that the future of global warming is still within our control. We have agency as a global society in controlling what those temperature changes will be and what the impacts will be going forward. And so we control what is going to happen. It isn't foregone conclusion. We can control emissions, and by controlling emissions, we can control the future of global warming. Now, all of this is done with climate models, and as I mentioned, these climate models are wrong, they're imperfect, and they have some particular issues. So let me just briefly go through what's wrong with climate models. These models have systematic biases, so they have a tendency to rain where it shouldn't rain, they have a tendency to have it not rain where it should rain, etc. Their climate sensitivity has a wide range, so we don't know exactly what the total global mean temperature change will be as a function of increasing increasing carbon dioxide. Some of the regional and local changes are not robust across the model ensembles. It may be because these things are not predictable, but it may also be because the models are too noisy because of things like insufficient resolution, incompleteness, or basic structural error in how we've done these things. The number of scenarios that you might want to explore. I showed you 4 scenarios. Well, obviously, what could happen in the real world is obviously more multifaceted than just 4 storylines. So we really need to do a lot more to span those possibilities. And so we don't because the models are too slow. We haven't done enough work on policy-specific scenarios. What would happen if we changed this? And those are the kind of things that are like super useful to decision makers and policy makers around the world, and we haven't done enough of that. And I think the most important is that we have done a very poor job in having the information that's contained within climate models be translated into useful estimates of adaptation potential, mitigation potential, resilience. We haven't used the information that we have to the maximum extent that we could. And there are lots of different needs for climate projection information, given all of the caveats and all of the approximations and all of the uncertainties. But there's a lot of decisions that are being made that are not using any information, whereas even a little bit of information would be useful. And the reason why we have all of these problems is that basically the models are too slow. They're too complicated, there's too much computation, and they take massive amounts of models, massive amounts of computation to run these things. So what are the future directions? So people want to have higher resolution and greater complexity. That comes at a cost. Some of that cost can be offset by new efforts in machine learning to do better downscaling from the model grid boxes to the local environment. Machine learning to improve the prioritizations using more data to make more accurate process-based model. To do the tuning, I mentioned that earlier. To do the scenario filling using emulators. We can do a better job with that even now than we have done up until now. So that gives us That's a little bit of a counterpoint to the increasing complexity and resolution. But we also want to do more ensembles. We need to do more initial condition ensembles to sample the weather and get a bigger mass of climate models that sample all of the different states of the weather at the same time. We need to explore the uncertainty in the forcings, in things like the aerosol emissions, things like the solar forcing. And then we need to look at the structural uncertainty in the models themselves by perturbing the physics, by putting in different parameterizations, different tunings of parameterizations, and seeing how they affect the climate sensitivity or the projections. But most of all, we need more and better observational constraints. A lot of the uncertainty that we have is because we don't have sufficient observations of things like aerosols in the atmosphere, of things like the water on land and the changes in gravity, and all of the things that we are measuring, we're trying to measure now. We have there's two new satellites that have gone up that I think will be extremely useful for constraining models. There's the PACE satellite, which is a NASA joint NASA Dutch effort to measure both changes in the ocean but also changes in aerosols in the atmosphere, and then EarthCare, which is a project from the European Space Agency, which is going to be able to measure the interactions of clouds and radiation and aerosols all together, and all of those things are going to be enormously useful in the years to come to constrain these models. But we need bigger efforts. We need things like national or international scale investments in data analytics, places where all of the data can be put, all of the observational data, all of the satellite data, all of the weather forecasts, all of the climate models, and we can analyze them in intelligent ways to just kind of improve the parameterizations, improve the processes, understand why the models are wrong, where they're correct, where they're not correct, and then have that information be available to people who are downstream of the models, people who are making decisions based on climate adaptation efforts or trying to work out what the impact of climate mitigation would be. And we haven't got this, right? So right now, data is nominally available. You can go and download lots and lots and lots of data, but to have it all in one place, it's petabytes and petabytes and exabytes of data, and you cannot download that onto your home computer. It has to be sitting in the cloud somewhere, in a cloud somewhere, and everything has to be available. And the way that we've got it set up now with the commercial cloud means that we're not going to get that. So in Europe, there's this project called Destiny or Destination Earth, and they're trying to set up a data lake where, for the Europeans, all of that information will be be available, but it will only be available for the Europeans. And so if the Japanese or the Americans or the Chinese want to have access to that kind of capability, unfortunately they're going to have to do it themselves. This is really the cutting edge of what's needed, both for using large-scale machine learning, both for improving adaptation and building climate resilience. People talk about digital twins for climate as part of that same kind of effort, and I think it's worth being a little bit hesitant there. Are we going to get higher resolution weather forecasts using machine learned weather forecasts? The answer is yes, we've already started to see that. Are we going to get better decadal climate predictability? Very unclear whether that's going to happen because of quite subtle things, but it's very unclear. Are we going to be, is that going to give us an effort, is that going to allow us to better integrate with impact models that are being run at local cities or by water resource managers? Maybe. That's very hard and really requires work, but maybe that will happen. We are going to see better data visualizations, there's no question. Are we going to see more interactive user engagement with the data? Yes, we may be able to see that. But digital twins of climate are not the panacea that people are sometimes discussing. We're not going to have purely machine-learned climate predictions that are only taken from the observations. That is not going to happen because you need to have the physics to be able to make constrained predictions out of sample of the data that you have used in your training. So improving the skill and usability of climate predictions is a very important goal, but we have to remember that multi-decadal climate projections are a boundary value problem. We're not trying to predict the weather so much, we're trying to predict the statistics of the weather, and they change as a function of things like carbon dioxide and aerosols and the like, and that can't be learned from the weather today. It can only be learned from the climate change, and we haven't had enough climate change in the observed period for us to be able to train machine learning models on climate change. Better weather forecasts don't automatically produce better climate forecasts, and there's no clear resolution, there's no clear connection between having more and more details and having a change in the sensitivity. And so that means that having more and more details doesn't necessarily get you to a point where you're going to converge on the right number. But we can do better. We can reduce systematic biases. We can constrain things using physics and observations. And we can clearly do a better job with usability. Can we do better data analytics? Can we do better downscaling? And I think all of those things, the answer is obviously yes. So, to address the questions that we started with, what are the drivers of climate change? Us. We are the drivers of climate change. Society, deforestation, burning of fossil fuels, air pollution, all of these things are because of us, and those are the trends that are driving the trends in climate. Are things changing faster than we predicted? Not yet. Obviously, that is always subject to new data coming in, but as far as we can tell, things are changing, unfortunately, pretty much as we predicted. And where do we go from here? The key result is that it is still up to us. We are not on a runaway train. We are not going to see a runaway greenhouse effect. The changes that we're going to see in climate are due to the emissions that we are going to put into the atmosphere. And let me finally finish with a quote that it speaks very clearly to the situation that we're in right now. This is from Sherwood Rowland, who won the Nobel Prize for chemistry for discovering the reactions that led to ozone depletion. And this was an interview a number of years later, and he says, "What's the use of having developed a science well enough to make predictions if, in the end, all we're willing to do is stand around and wait for them to come true?" And that encapsulates exactly our situation. The as a scientist, you're supposed to be happy that we've understood something from the universe, that we have encapsulated it in our models, and then we've made predictions that turn out to be successful and true. And yet, the predictions that we're making, we don't want to come true, right? So we're stuck, the scientists involved are stuck in being happy that we understand something about the system, and then being unhappy that we understand something about the system and what the consequences of that are. And so most climate scientists around the world are now grappling with this issue. What are we supposed to do when we see our predictions, but we don't want them to come true? And so we have to talk about what's going on. We have to engage with people who might not believe us. We have to try and help people who want to make better decisions. And eventually we will prove ourselves wrong because we will have altered the course of our trajectory. And that is the main reason why I speak to you today, and I speak to other people every other day to talk about what's going on. We do not want to stand around and wait for these predictions to come true. We have to act. Thank you very much.